Okay, so welcome back, and now what we're going to do is we're going to do a proof of the ratio test. And so again, there's three cases we're going to go over, and so let's start with the first case. So we're going to let this be a series of non-zero terms. And so case one is where rho is less than 1. Okay, so case one is where rho is greater than or equal to 0 and less than 1. Okay, and since we're assuming the series is a series of non-zero terms, then being greater than or equal to 0 is true. Okay, so case one, rho equals the limit n approaches infinity of the absolute value of n plus 1 over a sub n is less than 1. And since rho is between 0 and 1, right? So since since rho is between 0 and 1, there exists a real number r such that this has to be true. Okay, so all I'm saying is that since rho is less than 1, then there has to be existent r such that rho is less than r, which is also less than 1. And so we're going to let epsilon, now we're going to define epsilon in terms of rho and r. And so now I'm going to let epsilon equal the difference between r and rho, which is going to be positive. And so by definition of the limit of a sequence, there exists an integer n. Okay, so now we're going to use the definition of a limit. And so we know, based on this, we know that there exists So we know there exists n, right, in some integer n. Let me be exact. Such that, what must be true? Well, the absolute value of the difference, right, between where we're going, right, r, or rho rather. So the absolute value and this, right? So it's going to be an plus 1 over a sub n minus rho, right? So this absolute difference must be less than epsilon, right? For all n greater than or equal to n. Okay, so that's just using the definition of limits, limit of a sequence. Okay, now, therefore, what does this give us? Well, that means that using this, then that means that the absolute value of a sub n plus 1 over a sub n is going to be less than epsilon plus rho, which equals hold on. Yeah, that's right. And what is this equal to? Well, this is equal to what? R. So this is equal to R. And this is true for all n greater than or equal to n. Okay, now, what does this give us? Well, now, watch what we can do. Okay, so now, then, what's true? Well, that means the absolute value of an plus 1 right? So capital N, well, then that must mean that that's going to be less than R times the absolute value of a sub n. Oops. Well, if that's true, then we can say that the absolute value of a sub n plus 2 is less than, oops, R times a sub n plus 1. But then, because of this, this has to be less than R squared times a sub n, right? And then if I go one further, and I say, okay, well, a sub n plus 3 obviously has to be less than R times, oops, a sub n plus 2, which is then has to be less than or equal to R squared times the absolute value of a sub n plus 1, which is less than R cubed times the absolute value of a sub n. And you see how this is going, right? And it just continues on in like fashion, right? Now, since r is less than 1, okay, we said that in the beginning, right? We defined r is less than 1. The geometric series which is given above well, not given above, but given by this. Oops. Okay, and you'll see the comparison here in a minute. Oops. Okay, so since since r is less than 1, this geometric series converges, right? So this geometric series converges. Now, you might see where I'm going with this, okay? And then given the inequality above, right? Given this inequality above, we can use the comparison test. And we can conclude that the series I have to erase this. Give myself some more room. And so we can conclude by using the comparison test oops. Also converges. And then therefore, since let me get rid of this. Now, so therefore, since we can rewrite our series oops, okay, so since we can write our series like this, we can write it as the sum of two other series. Now the first series is finite, right? It's just a finite sum. And the second series in the sum converges by the comparison test above. So we can conclude that the series of a sub n, the absolute value of a sub n from n equals 1 to infinity converges. And that's what I want to write. So since, therefore, since this equals this, right? And this is a finite sum. Okay. And this series converges above by the comparison test. So then the series converges. And that's the end of part 1. Okay, we'll come back and do part 2.